let's solve some more examples. We are not going to do anything else this week. We'll just solve examples. So is the issue really important enough to disrupt the course? All right. Now, let's solve something about angular momentum conservation. So here's a hockey puck. Do you know what a hockey puck is? It's basically the ball in ice hockey. Okay, but it's a cylinder which is going with velocity v, and omega is equal to 0 on ice, which is more or less frictionless. And then it actually hits a small piece of dirt, m, where the initial distance between the center of the puck and mass is b. So after the hit, m sticks to the puck. So I'd like to find out two things. First is v prime. The other is omega prime. So after the small mass is attached to the puck, it will change its velocity. It's also going to change its rotation. It will start rotating around itself, right? So I'd like to calculate both of these quantities. Now, let's be very careful. I'm actually not asking for the velocity of the center, but I'm actually asking for the velocity of the center of mass of the full system. Okay, so I should tell you what the hockey puck mass m is, what its radius is, and I can tell you that from its own center of mass, the puck's moment of inertia is mr squared over 2. Does everyone understand the question? We are looking at the ice from the top. We have a hockey puck that's moving with velocity v, but not rotating around itself. And it hits a small piece of dirt on ice, and that piece of dirt sticks onto the puck. What do we expect? Now the puck is not balanced, right? I mean, its center of mass is not the geometric center of that circle. So its center of mass is going to move on a straight line, but it's also going to rotate around the center of mass. So we need to calculate the velocity of the center of mass of this new object, and also the angular frequency of rotation around that center of mass. What are our conserved quantities here? Frankly, we have only learned 3 conserved quantities, right? Energy, momentum, and angular momentum. So during this collision, which of the 3 conserved quantities is actually conserved? Who thinks energy is conserved in this collision? Excellent. No one thinks that, because this is a completely inelastic collision, right? So we know that for that piece of dirt to stick to the puck, some new molecular bonds have to be formed. Some energy must be dissipated. How about momentum? Do you think momentum is conserved during this collision?
Yes.
Yes. Why? Because this is a closed system. There are no external forces on the puck or that piece of dirt, right? So this is a closed system. for momentum, which means total momentum, is conserved. I must have momentum conservation. Now, if there are no forces, that also means there are no torques on my system. No external torques. So, angular momentum must also be conserved.
Can we say that if momentum is conserved, angular momentum is always conserved?
Angular momentum is not always conserved. If momentum is conserved, I can find some specific examples to disrupt that, but they'll be more advanced. So it's better to look at them separately. Okay, you're right that in all the questions what we are going to consider in this course, if momentum is conserved, angular momentum is most likely conserved. All right. One example I can sort of tell you is that when two masses like that hit each other, okay, what happens is that initially I had some angular momentum, and my final angular momentum is not going to be equal to the here momentum will be conserved, right? So I'll have mv, let's say 0. I'll again have mv here. But angular momentum is not going to be conserved because there will be torques coming from the floor. Okay, there will be no net force on that, but there will be torques there. All right. So do not generalize. Please look at the system separately. Okay. Now that's a good question, by the way. Now momentum is conserved. So what was my initial state was following. My initial state was I had v and this guy has m. Small m does not have any velocity, so my initial momentum is mv. How about my final momentum? Well, my final momentum is the following. My final momentum is, if I want to find the v center of mass, my final momentum is always total mass times velocity of the center of mass. Okay? Now, if initial momentum is equal to final momentum, then v center of mass is just capital M divided by m plus small m times initial v. I think we call this v prime though. No, v center of mass, good. But how about angular momentum? So I have small m here, and omega is 0. Now, whenever I think about angular momentum, I must always ask, according to which axis? Right? That was the most important thing. Whenever I actually talk about angular momentum, I must specify my axis. Now, where do you think I should put my axis here? Is angular momentum conserved for all axes? Yes, it is, right? There are no forces, there are no torques, angular momentum. So wherever you put your axis, if you calculate your angular momentum correctly, you will actually find that it's conserved. However, I want to choose a point which will make my calculations easier. Which point do you think I should choose? Center of mass, right? That was the utility of center of mass. It actually makes my calculations always easier. So here's what I'll do. I'll choose an axis. I'll choose my axis exactly here. So that, let me call this distance L. L times m is capital M times b minus L. Right? Why did I choose that point? Because this is exactly where the center of mass of the full system moves before the collision. Right? That's going to be the y coordinate of the center of mass before the collision and also after the collision. Center of mass moves on that line before the collision and also after the collision. Right? Does everyone understand the logic here? The velocity of the center of mass, does it change during the collision? No, it doesn't, because the total momentum of any collection of particles is velocity of the center of mass times the total mass. The total mass doesn't change. So the center of mass always moves on a straight line. And that line, I can actually find out where it is by just thinking about where the y coordinate of the center of mass. So I'll find L to be what? M divided by m plus capital M times b. So that will be my L. So according to that point, what is my initial angular momentum? It's going to be R cross P plus I times omega, right? That's how I actually wrote the angular momentum of any object. But what is I times omega? First of all, there is a small mass and a large mass. Small mass is not moving, so it's not contributing any angular momentum. So that has to be for the large mass. Now, R cross P. What is R here? R is the vector from my axis to the center of the puck, right? So that will be my R. And this is V. So, what is R cross P? R cross P is, that angle is theta, R magnitude times sine theta times m times V. And I omega is 0 because omega is 0 initially. Okay? But R times sine theta is what? R times sine theta is exactly this length here. So it's going to be B minus L. So it's going to be B minus L times mv. And I know what L is. It's going to be 1 minus capital M or small m plus small m times mbv, which tells me it's small m times capital M divided by small m plus capital M times b times v. That is my initial angular momentum. How about my final angular momentum? here is the situation now. I have this puck plus small mass system. But I know the following. I know that its center of mass still keeps moving on that line, and my axis is here. Axis is on center of mass. Right? But now, so what's my L final? L final would be R cross P plus I times omega. But what is the R vector here? R vector is the vector from the axis to the center of mass. So it will be somewhere on this line. I mean, exactly in this situation, if in the moment of collision, that R vector is 0. Actually, at any time, because MV is parallel to R, that is 0. I'm just left with I omega, and that's why I chose center of mass. If I chose any other axis, in one case, I would have to calculate I omega. In the other case, I would actually have to calculate R cross P. So center of mass helps me twice. What is I times omega? This is the moment of inertia of the puck? No. It's the moment of inertia of the full puck plus small mass system around the center of mass. So let's write this down. This is the moment of inertia of puck plus m around the common center of mass. What is that? Now I can certainly calculate it. That length is r. So here is my center of mass. If I call this distance x, I know that x times capital M is r minus x times small m, right? So I can find x as m divided by m plus capital M times r. So what is I center of mass? There are two contributions. One contribution is from the small mass. Small mass contribution is m times r minus x squared. Plus, there is a contribution coming from the puck. And how do I calculate the contribution from the puck? By the parallel axis theorem. It's going to be the center of mass of the puck moment of inertia plus m times x squared. So let's calculate all of this. This is going to be m times r minus x. In that case is what? R minus x is 1 minus m plus m times r. So it's going to be capital M over m plus m times r. So m times capital M square over m plus m square times r square plus m r square over 2 plus m small m square divided by capital M plus small m square times r square. So let's calculate all of these in a nice way. I'm going to say this is r square times. Let me take a factor of capital M out too. M over m plus small m squared plus 1/2 plus small m square times squared. Let me play around with it a little bit more. I have 1/2 plus small m plus small m divided by m plus small m squared. So 1 power of that cancels. And that is m r squared m plus 2 small m divided by 2 times m plus m. Okay? So now I omega is omega prime. I think I called it. Yes. Equal to initial angular momentum, which we calculated here. Li, which is equal to small m plus capital M, small m plus divided by, maybe not that, right? Small m divided by times B times V. Yes. Should that be 3m? Let's check that out. I'm multiplying. This is 2m. This is m. It should indeed be 3m. Thank you. Okay. So m times m plus 3m divided by 2m plus m times r squared times omega prime is m times capital M, m plus m times B times V. So omega prime is what? Omega prime is m divided by capital M plus 3m times 2 bv divided by r squared. Did I reach my goal? Yes, I did. Everything here was given. Let's check the units though. Let's check the units. So goal is okay. What do I expect omega's unit to be? 1/2. So here, what was B? B was the length between the center and basically how much I missed the center with small m. So B is meters. So let's say this is kilogram divided by kilogram. Meters times V is meters per second divided by meters square. So units also check. That's 1/2. How about the limits? What do you think happens when B is equal to 0? When B is equal to 0, I'm actually hitting that small mass head on. Would I rotate? There would be no rotation. B is equal to 0 should give omega prime equals to 0. That checks, so that's good. Similarly, if M goes to 0, omega prime should go to 0, and that also checks. But, quite easily I could have made a mistake in the coefficients. I already made a mistake. If your friend did not correct me, I would have said that would be m plus 2m, right? So please be careful with your numbers during the calculation. If you're missing some analytical factors, some, capital M, some omega, that you can figure out by eventual dimensional analysis, eventual unit analysis. However, if you're missing 2, 3, or instead of 3, if you wrote 2, you will not be able to correct this by our unit check method. All right? Any questions? Louder, please. Final angular momentum up. Okay, yeah. Here. Not, I mean, if I choose my axis to be on that line where center of mass moves, it's always going to be 0, yes. But if I choose it somewhere else, then I'll actually have to calculate that factor. That's why, I mean, initially when you look at this problem, the way I started my solution is maybe a little bit counterintuitive. Why do I not put my axis at the center of the puck or on the mass itself? Because if I do that, then I would have to calculate two more things. I would have to calculate R cross P for the whole thing. Okay? All right. Let's solve one more question. Any comments? Any questions? I mean, one thing you should be able to do is look at the question and tell what are the conserved quantities. Okay? Is angular momentum conserved? Is momentum conserved? And is energy conserved? I think the simplest one is energy. Energy is conserved whenever there are no non-conservative forces. For this course, it means if there is no friction, energy is conserved, right? How about momentum? You must be very careful with momentum conservation. The net external force on my system has to be 0, right? And angular momentum, I think that's the hardest one, okay, because you have to define angular momentum with an axis. If there is a given pivot point in your problem, if you know that one point in your problem is going to stay fixed during that problem, then it's best to define angular momentum with respect to that point. But if everything is moving freely, as in this problem, then choosing your axis is very important. It actually may simplify your calculations, or it may make it really hard. All right? Good. Let's solve another example. Simple one now. So I have a rod which was initially it's fixed from one edge, which was initially vertical, and I let the system go and it falls. What I would like to find out is when it falls, exactly before it hits the ground, what is omega? Okay? What is conserved here in this problem? Energy is conserved. Is angular momentum conserved? No, it's not conserved. Why? Because there is mg acting on the center of mass, which creates a torque with respect to my pivot point. Okay? How about momentum? Obviously not conserved, because there is the pivot point which is giving some forces, okay, which is not only canceling mg, but it's also canceling canceling the lateral motion, right? So the only thing I actually have to do is energy conservation. Can you tell me the initial energy of the system? If I choose my reference point, reference level, to be the ground level. Initially, I only have, okay, I should give you the mass and L of this homogeneous. mgl over 2, because my potential energy, I can think that it actually acts on my center of mass. How about the final energy? Is there any potential energy? No. So, do I have any translational kinetic energy?
inside of the rotation.
Okay, so let me do it two ways. One way is to say, hey, I know that there is a pivot point. That's actually going to be constant. So all the motion I can actually analyze as rotation. So what I will say is that that is going to be 1/2 I edge times omega square. So, and I edge I'm given as 1/3 ml square. So if I equate these two, energy initial is equal to energy final. mg L over 2 is 1/2 1/3 m L square times omega square. M's cancel. 1 power of L cancels. 1/2 cancel. Omega is square root of 3g over L. Okay? Let me write it in another way. I told you that this works if I'm sure that one point does not move. And here I'm sure that the edge does not move because it's pinned there by a needle, right? By some nail. Now, what if I actually write it in another way? I said the correct formula is, the formula which is always correct is 1/2 m times v center of mass square plus 1/2 I center of mass times omega square. Now, if I have omega, what would be my v center of mass? That length is L over 2, so it will be L over 2 times omega. So my final energy I could write as 1/2 m L over 2 squared times omega squared plus 1/2. What is I center of mass? ml square over 12. And if I combine these two now, I have 1/2 m over 4 plus m over 12 L square omega square. What is this? M over 3, right? So and this is exactly what I have here. So that way of calculating things is always correct, okay? But if you're sure that one point in your problem doesn't move, you can regard all the motion as rotation around that point. Okay? Good. Let me change the question slightly. Now I have frictionless plane. And I'm leaving a rod, a uniform rod, initially vertically. What will happen to it? It's going to slide and go down. So the question is, as it hits the floor, what's the velocity of the center of mass? First of all, how far to the right, does the center of mass move during this motion? It doesn't move, right? There are no forces in the horizontal direction. So essentially your center of mass falls to exactly where your initial contact was. There's a question. Okay. So how do I solve this problem? Yes.
We know the angular momentum, angular speed, therefore we can
How do we know the angular speed?
calculate it.
Yes, but that was for a different problem, right? That was for a problem where one edge was fixed. Here, that edge is also moving, right? So I can't really just say that. Maybe by using Newton's equations, that's right. But energy is conserved, so can I somehow relate energy conservation? I don't know.
We can find image conservation.
So here is the thing. In an intermediate point before the fall, what does the system look like? The system will make some angle with the original line here, right? And I'm sure of the following, that I did not draw this very well. Can it be just translational motion? No, I think you really have to rotate to fall down, right? So I know that, okay, yeah. So the center of mass center of mass cannot move to the right or to the left, right? So at any point, if that is my y, the angle I make with the horizontal, theta, is not independent of y. I know the following. I know that L over 2 times sine theta must equal y. Where did I get this from? This is just center of mass does not move along x. Or in other words, this is momentum conservation. Good. Now, what does this help me with? It helps me with the following. If I take a derivative of this expression, take a time derivative, d by dt of sine theta is, so L over 2 is a constant. The derivative of sine theta is cosine theta, but I need to use the chain rule. I need to write d theta dt is dy dt. dy dt is vy, and d theta dt is what I call omega. So at any angle theta, vy, and omega are related. Okay? So, what is my initial energy? My initial energy is, if I choose my reference level to the ground, m times g times L over 2. So what is that equal to? Initial energy is equal to final energy. It must be mg L over 2 must equal what? Mg L over 2 must equal 1/2 m v center of mass square plus 1/2 I center of mass omega square, right? That's always correct. But now I know that V center of mass must equal Vy. Why? Because there is no motion in the x direction, right? Oh, that's great. So this is equal to 1/2 m Vy square. And the nice thing is also for omega, I actually know the relationship between omega and Vy. Omega is apparently 2 over L 1 over cosine theta times Vy. So I can actually write this for 1/2. I center of mass is ml square over 12. And omega is 2 over L 1 over cosine theta Vy square. But at which theta am I writing this? Well, it's actually correct at all theta, but I'm interested in the velocity when you're right about to hit the floor, right? And for that, theta is equal to 0. So at theta equals to 0, cosine theta is 1, which means mgl over 2 is 1/2 m Vy square plus 1/2 m L square over 12, 4 over L square, 1 over cosine square theta, which is 1, times Vy square. L squares cancelled. That gives me a 3. So it gives me 1/2 m 1 plus 1/3 Vy square is mg L over 2. 2's cancel, m's cancel. Apparently, Vy is square root of 3/4 GL. All right? Yes, question. Oh, when theta is 90, I'm in the vertical situation. And at that point, what's my Vy? My Vy is 0. My omega is also 0, so there is no problem with that definition. Louder, please. I cannot really hear you. That is correct, yes. Well, I mean, I wouldn't say it's undefined. I would say that equation works when theta is larger than 0. Or theta is actually less than pi over 2. Yes? Excellent question. Why does the center of mass not move? What is the total momentum of this object? Total momentum of this object is its total mass, m, times its velocity. And it has two components, in the x direction and in the y direction. Are there any forces in the x direction in this curve? There are none, which means the x component of momentum must be conserved during the motion, which means velocity of the x component of the center of mass must be 0, which means the position of the center of mass along the x direction must be conserved. All right? I mean, if you're, maybe Bilkent was too easy for you. You're relaxing too much. Try to do the same problem with friction. Okay, assume that there is some friction and see how much you will move. Yes, another question. Yes, and that force is exactly normal. I'm not putting any lateral force on the surface. Think about it. That would mean friction, actually. Another question? No? Let's finish the lecture. If you have more questions, you can come and ask me.